So before we actually did the definition of derivative. And the definition of derivative was the limit as delta x approaches 0 of what? F of x plus delta x, and then minus f of x all over delta x. And what was a derivative? Slope of a tangent line. And so what we kept doing is we found slopes of a tangent line, or an equation that gives me the slope of the tangent lines at certain points. And we use this definition of derivative with our lovely algebra skills that we're all really good at. And so then, this is the alternate form of definition derivative. It's still like y2 minus y1 over x2 minus x1. However, this one comes up into play sometimes. Instead of doing a limit as delta x approaches 0, this is a limit as x approaches c. It approaches a number. And then it's just f of x, the function, minus when I evaluated at that number over x minus c. And so this is an alternate form of a derivative. I didn't used to teach this very much because it didn't show up on the AP exam. However, every now and again it's starting to show up more on the AP exam, so we have to be used to it now. So on this one, again, what's a limit though? What's a limit? When you do what? When you approach from both sides. All right, and so when we still have to get that concept in because we're still taking a limit from both sides when we do an x approaches c. So let's look at this one. We have our greatest integer function. All right, I'm using some examples here with our alternate form of derivative to kind of hit some concepts about continuity and differentiability today. All right, so it's some thinking, not necessarily a whole lot of math though. So we have this greatest integer function. And so is this function a continuous function?
Yes. No.
It's definitely not. It's definitely not continuous. All right, because what's happening? I'm lifting my pencil, exactly. So it's definitely not a continuous function. And what you want to say is if it's not continuous, it's not going to be differentiable. And I'm going to use the alternate form to show that it's not going to be a differentiable function. And so what I'm going to do is I'm going to look at 0. I'm going to look at 0. And so I'm going to use this alternate form of our derivative. And a derivative is really a what? Slope of a tangent line. Good. Here we go. So I'm going to use this alternate form. So if I substitute it in, I got the greatest integer, and I'm going to go from the left and the right because that's what a limit really does. And so if I do it a little bit from the left of 0, it's a really small what? Negative. Does everybody agree with that? Yeah. And so if I have a really small negative of a greatest integer x, what's it in between? -1 and 0. But is it reached 0 yet? No. And so what do we get? We get -1. And then -0 over a really small what? Negative. And so a -1 over a really small negative is what? Positive infinity. And so right away, you know your limit's not going to exist because it goes to infinity. However, if we're going to go from the right side, let's prove it more. And so now if I go from the right, 0 from the right of my greatest integer of x would be what? 0. Minus 0 over a really small what? Positive. And so a 0 over a really small positive is what? Is 0. Okay, 0 over any number is 0. And so, do they match up? No. But what I want you to see is if the function is not continuous, it cannot be differentiable. That's what I want you to write down. If the function is not continuous, it cannot be differentiable. All right, this next one is an absolute value function. And when we deal with absolute values, I'm always going to talk about the algebra of it first. Okay, I actually don't do the calculus method because we're all really good at algebra. I always do algebra and geometry with absolute values all the time. All right, and when we integrate things and when we take area under the curves, I'm still going to do it algebraically. But let's talk about this absolute value x, or absolute value of x minus 2. All right, this is a flying v. Does everybody agree with that? It's a mighty duck. All right. However, where is its problem area? Where does it touch? At 2. Using the zero product property, if I were to set that equals 0, it touches at 2. Yeah? And then what are my slopes? My slopes are what? 1 and -1. Because like if I had like the absolute value of like 2x minus 1, those would have slopes of what? 2 and -2. So if you actually understand the algebra behind the absolute value, the calculus is super easy. All right? And so if I take a derivative, because this is the alternate form of our derivative, the derivative from the left of 2 would be what? Negative 1. The derivative, what's a derivative?
Oh, the slope.
The slope of a tangent line. So the derivative of the left of 2 is what? Negative 1. The derivative to the right of 2 is what? 1.
Okay.
Because a derivative is a what? A slope of a tangent line. And this is the alternate form of a derivative, which means what? The slope. However, is this function continuous?
Yes.
Yes, it's totally continuous. I can draw this without lifting my pencil all day long. However, does it have a derivative? Does it have a derivative at 2? No, because from the left of 2, it's what? Negative 1. From the right of 2, it's what? 1. Do they match up? No. And so what I want you to write down is continuous does not always mean differentiability. And the first example is when it has a sharp turn. So now I have this function. I got x to the 1/3. I got x to the 1/3 power. And so I can draw that without lifting my pencil again. So that's a function that's continuous. However, it might have some problem areas, and that's what we're going to look at right here. So I'm going to use this alternate form of our derivative to kind of prove there's a problem area. Okay? That's what we're using it for. And so if I were to substitute in my function, I'd have x to the 1/3 minus 0, because 0 to the 1/3 is 0. And then I still have it over x. Now, let's use our algebra skills here. So, what's x to the 1/3 divided by x? X to the 2/3 in the what? In the bottom, exactly. So this is really 1 over x to the 2/3. I used some algebra right there. I subtracted powers, and so that's what it actually simplifies to, right? And so what's a limit, though, when you approach from both sides? So if I were to substitute in a really small negative or a really small positive, I have a number, a positive number, over a really small what? A really small positive. So I have a positive number over a really small positive, which creates what? Positive infinity. Good, Yamil. All right. And so I don't actually have a derivative. I actually have a vertical tangent line. And so this is a continuous function, but it's not differentiable because I have a vertical tangent line. Is if I have something differentiable, it is smooth. All right? It is a smooth curve. And so it doesn't have any sharp turns. It doesn't have any vertical tangent lines. It is differentiable. And if it's differentiable, it is always continuous. That's big. If it's differentiable, it's always continuous. However, does it always mean if does it go the other way? Okay? So if it's continuous, it doesn't always mean differentiable. But if it's differentiable, it is always what? Continuous. So what we're going to do is we're going to find the slope graphs of these functions. Okay? We're going to find the derivative graphs of these functions. That means the same thing. And so let's do it. Here we go. So what's the slope right here? What do you think the slope of it is right there?
1.
1?
Yes.
Agreed? How about like right here? What's the slope?
1.
1?
Yes. Yeah, I think so.
How about here?
1. 1.
How about here?
1. Still 1.
1? How about everywhere on that line?
1.
It's 1. And so that is my slope graph. So that's f prime. If that's f, f prime would be that. Because what's a derivative? It's slope of a tangent line. All right, let's do it again. Here we go. So on this one, what do you think the slope is at -2? And I'm okay with issues.
Negative 2, I would say. Give me 3.
-3? I'll go with -3. So it's definitely negative, true?
House.
All right. All right. How about right here? What's my slope there?
I would say still
Is it more or less slopey?
less.
It's less slopey, pure math term. But it's negative, right?
Yes.
All right. but it's less than the other one. Do we agree? All right. So I'm going there. How about right here? What's the slope right there?
0.
That is 0. That's going to be very important this year. All right. The slope at that minimum is 0. Purely 0. All right. How about here? What's the slope there? 1? I like that. That's good. How about the slope here? 3? 3, 4? 6, 7? All right. All right. All right. So that, if I connect those dots, that would be f prime. So that would be the slope graph of that function. All right. So Ethan, what's my slope right here? Like really close to 0. What's my slope there?
Like 1/2.
I feel like one half is like a very like.
No, that's pretty slopey.
This is slopey. True that? Like big what?
Big number.
Big positive or negative?
Positive.
It's definitely positive, right? But it's a big positive. Agreed? All right, I agree. All right. How about it like 1? What? A smaller positive. I totally agree. How about it like 2? It's still what? It's still positive, but what's it doing? It's still a smaller positive, yes? Over here, is that a positive or negative slope? It's positive. But is it less or smaller than the other one? Sorry, that's the same thing. Is it more or less than the other one? It's less. And so now I'm down here. And so if I were to connect them, that's my f prime graph. And what is an f prime graph? It represents the what? The slope of the original graph. Okay? All right, cool. Let's do 42 now. Let's do 42. All right. What's my slope on this one? What's my slope at -3? -1. I totally agree. How about my slope at -2? -1. What's my slope here at -1? -1. I agree. How about right here? Anybody? Does not exist. Why does it not exist? It's a sharp turn. So right there, it does not exist. But everywhere left of 0, it should be what? -1. Agreed? All right, now let's go to the right of 0. So, like right here, what should be my slope there? 1. How about my slope at 2? 1. How about my slope at 3? 1. How about my slope at 0 again? Does not exist. That's why it's open. But everywhere to the right of it should have a slope of 1. And so that's what f prime is. So on 45, what are my slopes everywhere? 1. Okay, and so my derivative graph should look like that. Okay, because all my slopes are 1. It was linear. All right, on 46, what are all of my slopes on 46? 0. And so it's basically the x-axis as my derivative graph. Okay, so that's what f prime should look like. On 47, what is it doing left of 4? It's going down. And so my derivative should be down here, left of 4. Does everybody agree? And then to the right of 4, what's my derivative here? What are my slopes? They're all what? They're all positive. And so it should be kind of looking something like that. All right, let's look at 48 now. So right here, what are my derivatives left of 4? They're -1. And so I should have my derivative graph being -1 left of 4. However, what's going on at 4? It doesn't, my derivative doesn't exist. Why does my derivative not exist at 4? Because it has a sharp turn. Good? Now, what's happening to the right of 4? What's my derivative to the right of 4? 1. Okay, because my slopes here are 1. And so they're all 1 except for at 4. So there is what my f prime would look like there. All right. What's my slope right here? Positive or negative? Negative. Okay, it's definitely negative. However, right here, what is that?
A little more negative.
It's more negative. Does everybody agree with that?
Yeah.
And then right here, it's going to be what? Even more negative. Even more negative. So what it's doing is it's kind of doing something like that. All right. And then on 49, what's this right here? Oh, sorry. So right here, is this positive or negative? Positive. How about right there?
A little bit less positive.
Less positive. And then it's a little less positive, right? And so what it's doing here is it's actually kind of moving like that. All right? Now, was my derivative continuous? No. Because this function was not differentiable because it had a what? A sharp turn. Okay? All right, let's look at 50. All right? So, on 50, what's my derivative here? Positive, because my slope is a big positive. How about right here? It's less positive. Mary, all right, so right here, what's my derivative? 0. So it's positive, it's big positive, then what? Small positive, then what? 0. And so what that's doing is it's going like that. Okay? It's going like that. And then what's it doing? This would be what? Small negative, then what? More negative, and then super negative. And so what that's doing is it's going like that. And that's what f prime would actually be doing.